In today's class, we'll be talking about three-phase power. So we will explore three-phase circuits. We will see voltages and currents in the circuit, and then we will calculate the power that we are delivering to some specific load. So first of all, let's take a look on some basic three-phase circuit. You can see such an example on this picture, and this is how we will model our three-phase circuit. In this experiment, we will simulate a three-phase circuit that has a resistor, a capacitor, and an inductor as a load. You can see that we have here three AC voltage supplies. They all have a common point here on the left, and they are producing a sine wave for the voltage. In a three-phase system, the phase shift between the voltages is 120 degrees. So if we define that one has zero phase shift, this will be our reference voltage. The two other voltages have the same amplitude, but they have 120 degrees phase shift. So if this would be line number 1, line number 2 would have 120 degrees phase shift, and line number 3 will have minus 120 degrees. So now let's take a look on how we can actually model a three-phase circuit and LT-spice, and how can we plot the voltages and currents in the circuit. So I will start with a new file in LT-spice, and I will create this circuit so that you know how to do it, and you can later follow the lab manual and do the simulation. We need to add three voltage sources, and we will define their properties. So now I'm adding a voltage source like this. I will add it into my circuit, and I will orient it so that I can arrange the three power supplies next to each other. I will first insert only one of them, and I will define its parameters, and then I will just copy the other two remaining sources. So now I have one voltage supply. Let's leave the name as V2. I will right click and select Advanced, and now I'm selecting that this is a sine wave voltage supply. I will use a DC voltage offset of 0, and amplitude, let's simulate a real AC power network. So the amplitude is 325 volts. Now you may be familiar with 230 volts, but 230 volts is not the amplitude, but this is the RMS voltage. So if I want to simulate proper values in a power network, in this simulation I'm required to enter the amplitude, which is 230 volts times square root of 2. So this is 325. Now frequency will be 50 Hertz. This phi is the phase shift. So I will say that this is my voltage that has zero phase shift. And now I have an AC voltage supply with my defined parameters. Now I will just copy the two other voltage sources in my circuit, so I am able to create an exact copy, and now I will just change the phase shift of my voltages. So let's define this as 120 degrees, and this as minus 120 degrees. We need to add the common reference point used in the calculation, and in my circuit it will be the common point of all those three voltage sources. and I will connect this to the common point. So my power network right now is connected in the star configuration. And on the right side I will add my circuit. So I will use, for example, 3 resistors to define a load, and I will make this a non-symmetrical load. So every resistor will have a different value. So I will have here, for example, 100 ohms, here I will have 200 ohms, and here I will have 300 ohms. Now we just finish connecting the circuit like that, and we just need to do the final step, which will be to configure our simulation. So we'll go to menu Simulate and Edit Simulation command. What we want to do is to perform a transient analysis, and we would like to see few periods of our sine wave. Since we have 50 Hz, the frequency is the frequency. The period will be 20 milliseconds. So let's say I'd like to see 6 periods of my signal. So I will enter the stop time as 120 milliseconds. Now we just place the simulation command somewhere, and we are ready to go. So just run the simulation. Now I will just magnify my chart like this, and I will just arrange the windows, and now we need to select what variables do we want to display. Now before we do that, we will probably name this symbols, these wires in our simulation somehow, so that we have not the default names of our nets here, but we have some human readable names. So I will just name that this first wire will be called L1, line 1. This will be line 2, and the third wire will be line 3. Now, there's only one reason why this is useful. That's if you name the wires, then you will see directly the voltages that correspond to those names. So it will not be some arbitrary name selected randomly by LTSpice, but the voltage here will be called VL1, here VL2, and so forth. So now let's rerun the simulation, and we can select our voltages. So now I will select V1 here. We see this is a sine wave. It has the amplitude of 325 volts, and the frequency would be 50 Hz, and it starts from 0 because phase shift is 0. Now if I do the same for L2, we see that this has a phase shift of 120 degrees, and L3 has a phase shift of minus 120 degrees. So those are the voltages, and here we can see a nice 3-phase network. This is exactly what you would see directly on the power network, for example, with a voltage probe and with an oscilloscope. We can of course add the currents here. We can see the current probe when I hover above the component. And we have the voltages, they are all the same, they have just a different phase shift. And from the theory we know that there will be 0 phase shift between voltage and current, because we have a resistive load. And by looking on the values, I can directly see that the current going through R1 will be larger than current going through R2, and this will be larger than current going through R3. So let's take a look on that. Here that I will add current in R1, current in R2, and current in R3. Now please note that this symbol that we see here for the current probe is going in the opposite direction to my voltage. So in the chart we will see that it looks like that the phase shift between my current and my voltage is 180 degrees. But we have a resistive load, the phase shift is 0. This is only due to the reason that here I measure the voltage, which this probe is positive, but the current probe is going in the opposite direction. So let's see that in more detail. Now this is obviously not very clear, so we can split this plane into two, and we can now move the voltages to one plane, and then keep the charts here for the currents. So what we can actually see here is that we can read our voltages. Right now I'm reading my voltage. Let's select, for example, the green curve, like here. This will be V1, and we can see the value of my voltage, so 325 volts. This is the magnitude. Don't forget that if I want to calculate the RMS value, I take the magnitude and divide it by square root of 2. And in the bottom half of my chart in currents, we can see that we have the current here, IR1, and it has also the magnitude here, the maximum value, but it looks negative. But again, let me repeat that this is only due to the fact that in LT-Spice the current probe here is pointing in the opposite direction than I would actually require in this circuit. So we can see that we have minus 2 point something amperes. Of course, it's a resistive load. We could calculate the value of the currents from the voltages and from the resistances. And we can see that here we have a difference between the current in R3, which is the gray one, current in R2, which is the magenta, and current in R1, which is the light blue curve. And right from the start we knew that IR1 would be the largest, then we would have IR2, and here we would have IR3. So in this chart on top we can see the voltage that is the so-called line to neutral voltage. So it is the voltage between some point in my circuit with respect to the common node, which in my case here is this common node of my power supply. Now in a three-phase network we quite often use also a phase-to-phase voltage, and a phase-to-phase voltage is the voltage between two lines. So for example between line 1 and line 2. And in LT-Spice we can do it as well. Now if you click on this wire, for example L1, now I hold the left mouse button, I drag the probe to the other wire, and now this has added the voltage difference between those two wires into my chart. So now I can again go to my chart, I can split my voltage here. This is the new curve that we had, and this is the line to line voltage. And in our three-phase voltage networks we have the line to line voltage equals to 400 volts. Again, 400 volts, this is the RMS value. So the maximum value you can calculate here is different. So keep in mind that 400 volts is not the maximum value, it is the RMS value. Now what you will do next is that you will take those circuits and you will simulate those circuits for different values of the components. So each of you will get some selected values. You will run the simulation and you will calculate the power. Now the equations are given in the lab manual. We have calculated them last week as well. If we do it in LT-Spice, it's very simple. We just multiply the voltage by current in the time domain. So for example, if I would like to calculate how much power is being delivered to my resistance here, R1, I will multiply the voltage here times the current. So we just add a trace, and then here we add the expression that is doing this correctly. So we've done this last week, so we'll not repeat that today in the video. So now you will be given individual values, and your task is to calculate the powers, and then at the end to learn something about compensation of active power, which is done by adding a capacitor in the circuit. So here you see an example of such a circuit that you should simulate. We have a three-phase power supply. This is my load. It's a resistor and an inductor, which simulates a real inductive load. And by adding capacitors in my network, we can decrease the amount of reactive power that is being transferred back and forth from the network. So in real applications, it is quite important to compensate for inductive loads, and this is done especially for larger loads such as factories. So now it's up to you to simulate this and to find out that this really works.